Gravitation. As we have learned, the phenomenon of gravitation was discovered by Sir Isaac Newton. As the story goes, he discovered the force by seeing an apple fall from a tree on the ground. He wondered why all apples fall vertically downwards and not at an angle to the vertical. Why do they not fly off in a horizontal direction? After much thought, he came to the conclusion that the earth must be attracting the apple towards itself, and this attractive force must be directed towards the center of the earth. The direction from the apple on the tree to the center of the earth is the vertical direction at the position of the apple, and thus the apple falls vertically downwards. Figure above shows an apple tree on the earth. The force on an apple on the tree is towards the center of the earth, that is, along the perpendicular from the position of the apple to the surface of the earth. The figure also shows the gravitational force between the earth and the moon. Keep in mind that the distances in the figure are not according to scale. Newton thought that if the force of gravitation acts on apples on the tree at different heights from the surface of the earth, can it also act on objects at even greater heights, much further away from the earth, like, for example, the moon? Can it act on even farther objects like the other planets and the sun? No, it cannot. Use of ICT. Collect videos and PPTs about the gravitational force of different planets. Circular motion and centripetal force. Try this. Tie a stone to one end of a string. Take the other end in your hand and rotate the string so that the string moves along a circle as shown. Are you applying any force on the stone? In which direction is this force acting? How will you stop this force from acting? What will be the effect on the stone? As long as we are holding the string, we are pulling the stone towards us, that is, towards the center of the circle, and are applying a force towards it. The force stops acting if we release the string. In this case, the stone will fly off along a straight line, which is the tangent to the circle, at the position of the stone when the string is released, because that is the direction of its velocity at that instant of time. You may recall that we have performed a similar activity previously in which a 5 rupee coin kept on a rotating circular disc flies off the disc along the tangent to the disc. Thus, a force acts on any object moving along a circle, and it is directed towards the center of the circle. This is called the centripetal force. Centripetal means center-seeking. That is, the object tries to go towards the center of the circle because of this force. You know that the moon, which is the natural satellite of the earth, goes round it in a definite orbit, right? Well, the direction of motion of the moon as well as its speed constantly changes during this motion. Do you think some force is constantly acting on the moon? What must be the direction of this force? How would its motion have been if no such force acted on it? Do the other planets in the solar system revolve around the sun in a similar fashion? Is similar force acting on them? What must be its direction? From the above activity, example and questions, it is clear that for the moon to go around the earth, there must be a force which is exerted on the moon, and this force must be exerted by the earth, which attracts the moon towards itself. Similarly, the sun must be attracting the planets, including the earth, towards itself. Kepler's laws. Planetary motion has been observed by astronomers since ancient times. Before Galileo, all observations of the planets' positions were made with naked eyes. By the 16th century, a lot of data were available about planetary positions and motion. Johannes Kepler studied these data. He noticed that the motion of planets follows certain laws. He stated 3 laws describing planetary motion. These are known as Kepler's laws, which are given below. So let's have a look. Kepler's first law. The orbit of a planet is an ellipse with the Sun at one of the foci. This figure shows the elliptical orbit of a planet revolving around the Sun. The position of the Sun is indicated by S. AB and CD are distances covered by the planet in equal time, that is, after equal intervals of time. The positions of the planet starting from A and C are shown by B and D respectively. Kepler's second law. The line joining the planet and the Sun sweeps equal areas in equal intervals of time. The straight lines AS and CS sweep equal areas in equal intervals of time. That is, areas ASB and CSD are equal. Kepler's third law. The square of its period of revolution around the Sun is directly proportional to the cube of the mean distance of a planet from the Sun. Thus, if r is the average distance of the planet from the Sun and t is its period of revolution, then t square is directly proportional to r cube. That is, t square upon r cube is equal to constant is equal to k. Let this be equation number 1. Kepler obtained these laws simply from the study of the positions of planets obtained by regular observations. He had no explanation as to why planets obey these laws. We will see below how these laws helped Newton in the formulation of his theory of gravitation. Use your brain power. If the area ESF in figure is equal to area ASB, what will you infer about EF? No, EF is smaller. Newton's universal law of gravitation. All the above considerations, including Kepler's laws, led Newton to formulate his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force. This force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. This figure shows two objects with masses m1 and m2 kept at a distance d from each other. Mathematically, the gravitational force of attraction between these two bodies can be written as F is proportional to m1 m2 upon d2, or F is equal to g into m1 m2 upon d square. Let this be equation 2. Here, g is the constant of proportionality and is called the universal gravitational constant. The above law means that if the mass of one object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If the two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. In case when the bodies are not spherical and have irregular shape, then the direction of force is along the line joining their centers of mass, and d is taken to be the distance between the two centers of mass. From equation 2, it can be seen that the value of g is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, in SI units, the value of g is equal to the gravitational force between two masses of 1 kg kept 1 meter apart. The center of mass of an object is the point inside or outside the object at which the total mass of the object can be assumed to be concentrated. The center of mass of a spherical object having uniform density is at its geometrical center. The center of mass of an object having uniform density is at its centroid. Why did Newton assume inverse square dependence on distance in his law of gravitation? He was helped by Kepler's third law in this, as shown below. Let's have a look. Value of g on the surface of the Earth. We can calculate the value of g by using Newton's universal law of gravitation for an object of mass m situated at a distance r from the center of the Earth. The law of gravitation gives F is equal to capital G into capital M into small m upon r square. Let this be equation 3. Capital M is the mass of the Earth. F is equal to small m into small g. Let this be equation 4. From 3 and 4, small m, small g is equal to capital G into capital M into small m upon r square. Small g is equal to capital G into capital M upon r square. Let this be equation 5. If the object is situated on the surface of the Earth, small r is equal to capital R is equal to radius of the Earth. Thus, the value of small g on the surface of the Earth is small g is equal to capital G into capital M upon r square. Let this be equation 6. The unit of small g in SI units is meter per second square. The mass and radius of the Earth are 6 into 10 raised to 24 kgs and 6.4 into 10 raised to 6 meters respectively. Using these in equation 6, g is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 upon 6.4 into 10 raised to 6 whole square. So small g is equal to 9.77 meter per second square. Let this be equation 7. This acceleration depends only on the mass m and radius r of the Earth, and so the acceleration due to gravity at a given point on the Earth is the same for all objects. It does not depend on the properties of the object. Mass and weight. Mass. What is mass? Mass is the amount of matter present in the object. The SI unit of mass is kg. Mass is a scalar quantity. Its value is same everywhere. Its value does not change even when we go to another planet. According to Newton's first law, it is the measure of the inertia of an object. Inertia is the resistance of any physical object to any change in its state of motion. Higher the mass, higher is the inertia. Weight. Now, what is weight? The weight of an object is defined as the force with which the Earth attracts the object. The force F on an object of mass m on the surface of the Earth can be written using equation 4. Therefore, weight W is equal to F is equal to mg. G is equal to gm m upon r square. Weight being a force, its SI unit is Newton. Also, the weight being a force is a vector quantity and its direction is towards the center of the Earth. As the value of g is not same everywhere, the weight of an object changes from place to place, though its mass is constant everywhere. Free fall. Try this. Take a small stone. Hold it in your hand. Which forces are acting on the stone? Now release the stone. What do you observe? What are the forces acting on the stone after you release it? We know that the force of gravity due to the Earth acts on each and every object. When we were holding the stone in our hand, the stone was experiencing this force, but it was balanced by a force that we were applying on it in the opposite direction. As a result, the stone remained at rest. Once we release the stone from our hands, the only force that acts on it is the gravitational force of the Earth, and the stone falls down under its influence. Whenever an object moves under the influence of the force of gravity alone, it is said to be falling freely. Thus, the released stone is in a free fall. In free fall, the initial velocity of the object is 0 and goes on increasing due to the acceleration due to gravity of the Earth. During free fall, the frictional force due to air opposes the motion of the object, and a buoyant force also acts on the object. Buoyant force. It is upward force exerted by air upon a body. Thus, true free fall is possible only in vacuum. Solved examples. Example 1. An iron ball of mass 3 kg is released from a height of 125 meter and falls freely to the ground. Assuming that the value of g is 10 meter per second square, calculate first time taken by the ball to reach the ground, second velocity of the ball on reaching the ground, third the height of the ball at half the time it takes to reach the ground. Given m is equal to 3 kg, distance travelled by the ball s is equal to 125 meters, initial velocity of the ball is equal to u equals 0, and acceleration a is equal to g is equal to 10 meter per second square. First, Newton's second equation of motion gives s is equal to ut plus half at square. Therefore, 125 is equal to 0t plus half into 10 into t square, which equals 5t square. Or t square is equal to 125 by 5, which equals 25. T is equal to 5 seconds. So, the ball takes 5 seconds to reach the ground. Now, second, according to Newton's first equation of motion, final velocity is equal to v is equal to u plus at. Substituting the values, v is equal to 0 plus 10 into 5, which equals 50 meter per second. So, the velocity of the ball on reaching the ground is 50 meter per second. And third, half time is equal to t, which equals 5 by 2, which is equal to 2.5 seconds. Ball's height at this time is equal to s. According to Newton's second equation, s is equal to ut plus half at square. So, s is equal to 0 plus half into 10 into 2.5 square, which equals 31.25 meters. Thus, the height of the ball at half time is equal to 125 minus 31.25, which equals 93.75 meters. Escape velocity. We have seen that when a ball is thrown upwards, its velocity decreases because of the gravitation of the Earth. The velocity becomes 0 after reaching a certain height, and after that, this ball starts falling down. Yes, have you ever noticed that? Its maximum height depends on its initial velocity. According to Newton's third equation of motion is v square is equal to u square plus 2as. v is equal to the final velocity of the ball is equal to 0 and a is equal to minus g. Therefore, 0 is equal to u square plus 2 into minus g s, and maximum height of the ball is equal to s is equal to minus u square by 2g. Thus, higher the initial velocity u, the larger is the height reached by the ball. The reason for this is that the higher the initial velocity, the ball will oppose the gravity of the earth more and larger will be the height to which it can reach.
अगर आप अपने सिलेबस के सारे चैप्टर्स इस फॉर्मेट में देखना चाहते हैं तो हमें डिस्क्रिप्शन में दिए गए नंबर पर कॉल करें। ऐसे ही और एजुकेशनल वीडियोस देखने के लिए हमारे चैनल होम रिवाइज को सब्सक्राइब करें।